Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my pleasure to introduce Andy Pavlov, who's a PhD student about to graduate from Brown University. And so today he's going to talk about his adventures at the dog track.
Hey, thanks, Vivek. All right, thanks for everybody coming today. So he's right. I am going to talk about my two main passions in life, and that's the science of database systems and gambling on greyhounds at the dog track. Now, I realize, I hear some snickers. For a lot of you, these two things seem like they have nothing to do with each other whatsoever. But what I'm going to show today is that there's been specific research challenges or problems that we faced when trying to scale up database systems to support modern transaction processing workloads or modern workloads, where the answers to those problems have come directly from things I've either seen or learned or saw while at the dog track. So before I get into this, I want to do a quick overview of what sort of the state of the database world is right now for people that want to run for front-end applications. And I'll loosely categorize the types of systems that are out there today into three groups. So the first is what I'll call our traditional database systems. So these are things like DB2, SQL Server, Oracle, MySQL, Postgres. And the key thing about these systems is that they make the same architectural design assumptions and hardware assumptions that were made in the 1970s when the original database systems, System R and Ingress, were invented. Right? But obviously, a lot of things have changed since then. The second group is come around about the last decade or so, and these are colloquially referred to as NoSQL systems. So these are things like MongoDB, Cassandra, React. And these systems are really focusing on being able to support a large number of concurrent users at the same time, because they want to be able to support web-based and internet-based applications. And so for them, these traditional database systems weren't able to scale up to support their needs. And so my research is really focused on this emerging class of systems that has come about called NewSQL. And we're trying to have the best of both worlds. We're trying to maintain all the transactional guarantees that you would get in a traditional database system, but while still being able to scale up and support a large number of concurrent users in the same way that the NoSQL guys can. And so for this talk, I'm not really going to talk about the NoSQL guys other than to say that their work is complementary to ours. Right? So there's certain applications where you'd want to use a NoSQL system and not a NewSQL system, and vice versa. So now let's look at what one of these modern transactional workloads look like. So here we have a workload that's derived from the real software system that powers the Japanese version of American Idol. Now realize it's not called American Idol in Japan, but just go with me for this. And so in this application, what you have are people either calling in or using their laptops to go online and vote for contestants that they like on the show. And so when one of these requests comes in, one of these calls comes in, the application starts a transaction that will check in the database to see whether this person has called before and voted before. And if they haven't, it'll go ahead and create a new vote entry for them and update the number of votes that a contestant has gotten. Right? And so this seems like a pretty simple application. It seems like a pretty simple workload that really any modern database system should be able to support without any problems. So to test this hypothesis, we took two open source traditional database systems, MySQL and Postgres, and we tuned them for these type of sort of front-end transactional workloads. And we want to measure how well they can scale up and get better performance as we give them more resources. So on one machine, we're going to run the database system, and we're going to scale up the number of CPU cores that we're going to allocate to the system to process these transactions. And then on another node, we're going to simulate people calling in and voting for contestants. And what we found is, in both cases, both of these systems, they can't break past 10,000 transactions a second. Right? In the case of Postgres, actually the performance gets worse as you give it more CPU cores. And so I'm not trying to pick on MySQL and Postgres here, but I'll say that these results are emblematic to other performance results that we've seen in other traditional database systems. So we've done other experiments where we take Oracle and had to pay for a very expensive DBA to come out and tune it for us. And we see the same kind of results. As you add more CPU cores, you don't get better performance. So now the question is, what's going on? What is it about these traditional database systems that's causing them to not be able to scale up for what seems like a simple workload? So in another project in our research group, they took another open source traditional database system, and they instrumented the code to allow them to measure how much time is spent, or how many CPU cycles are spent in different components of the system when they run one of these transactional processing workloads. What they found is about 30% of the time is spent in the buffer pool. So this is managing an in-memory cache of records that have been pulled from disk and running some eviction policy to be able to decide when we need more room what to evict, what to write back out to disk. Another 30% of the time is spent in the locking mechanisms of the system. So because there's a disk, transactions could be run at the same time, and one of them could try to touch data that's not in the buffer pool, so therefore it has to get stalled while the record that it needs gets fetched in to main memory. So this all accounts for about 30% overhead, if you have to do this. Another 28% of the time is spent in the recovery mechanisms of the system. Right? So this is because we have an in-memory buffer pool, there could be dirty records that have not been safely written to disk yet. So they have to use things like a redo log or a write-ahead log and other mechanisms to make sure that any transaction that gets committed, all the changes are durable and persistent if there's a crash. You don't lose anything that's already been committed. So that leaves us a paltry 12% of time left over to actually do useful work for the transactions. So this is why these traditional systems are not scaling up. Right? Because we just simply have all this other overhead for all these other components. Right? And so where does that leave an application developer? Yes?
I don't quite see why that's scalability and not simply characteristic of even a unit processor system.
So your question is?
What's the multi-core angle on this?
So this is like if in a multi-core system, right? It's I see what you're saying. The question is, this is more emblematic to traditional systems rather than being a multi-core system. And I'll say, so like, the idea is that, well, in these type of workloads, you're usually CPU bound. Right? For these experiments here, it's a main memory database system. So there is no disk. Right? So that's why we're showing the CPU latencies. So this is just showing that if you want to be able to scale your system to support on these modern hardware with a lot of cores, as you start to scale them up, you think you'd get better performance, but you don't because you're paying still all this extra overhead to do all this locking stuff. You're shaking your head no. Sorry. Yes?
That's not the point. I mean, what says that the overhead can't scale per se?
The question is...
There's something else going on.
Yes, correct. Well, no, so it's... I mean, I'll come to this. Yes, there are other things, but the basic idea is that there is all this architectural baggage from the 1970s that all these three things are representative of. And so if you take a new look at what these workloads look like and what the hardware can do, what you can do with that hardware, then maybe you don't need these three things.
Should I think of the gray parts as having lots of synchronization primitives in them, and the green part as being like?
Absolutely. Yeah. So in the case, especially in the lock manager, right?
Okay.
Right. So if you have concurrent transactions,
That's kind of the answer, right?
locks, latches, and mutexes and other things.
That's the answer. The problem is not the overhead. It's the synchronization that's done in all of these.
But these types of operations, like maintaining a buffer pool, recovery, they may be inherently synchronization.
Right. You have to pin pages. Yeah. You have to.
Yeah.
Yes.
In order to prevent scalability, you would have to argue that the percentage of time spent in each of these increases as you increase the number of cores. It's not just a matter of having this overhead. If this overhead remained constant while you increase the number of cores, you'd get scalability.
Right. So let me go further, and then if you have more questions when I say sort of what our system is doing, we can talk about that. Okay. So where does that leave application developers? Well, up to, like I said, a few years ago, there's really only two choices. You could go with a traditional database system. And a lot of people do this because they provide the strong transactional guarantees, and it's actually easier to write programs when you have transactional semantics. But these systems are notoriously hard and notoriously expensive to scale up. So anecdotally, I'll say I have a colleague that works at one of the big three database vendors, which isn't Microsoft, and he tells me that one of their largest customers is a major bank in the U.S. that pays about $500 million a year, per year, just to run their transaction processing system. And for most companies, most organizations, that's simply infeasible. So for a lot of people in the last decade or so, we saw the rise of these NoSQL systems, right? Because they'll be able to get the better performance that you want to support internet and web-based applications, right? When you have a large number of concurrent users. But these systems achieve this performance over the traditional database systems by foregoing all the transactional guarantees that the traditional systems provide. So in the application, you have to write code to be able to reason with inconsistent or eventually consistent views of the database. So again, our focus is going to be on the NewSQL class of systems, where again, we're trying to have the best of both worlds. We're trying to be able to scale up and get better performance, and while still maintaining support for transactions. So the research problem we're trying to solve here is how can we actually do this? And what I'll say is we're not going to do this by being a general purpose system. Right? We're really going to focus on a certain class of applications that have key properties that we can exploit in our system. And we're not going to try to claim that would be a one-size-fits-all database system for everyone. And so the first question is, well, what are these properties in these type of applications that we're going to focus on that we want to have our system be optimized for, that we're really going to take into consideration? And so the answer to this first problem can be found actually at the dog track. So specifically, there's 3 important characteristics of greyhounds in dog racing and the type of transactions in the applications we want to support that are actually directly analogous to each other. So the first is that both of these things are very fast. So in the case of these, in case of greyhounds, they're the fastest one of the fastest animals you can have on the planet. They can run almost about 40 miles per hour. And similarly, our transactions are the fastest type of transactions you can have in a database system. So we're talking about transactions that can finish on the order of milliseconds rather than minutes or even seconds. We're not talking about long-running transactions. The second thing is that both of these things are very repetitive. So in greyhound racing, the dog just runs around in a circle on the track, and that's it, right? There's nothing else that it actually can do, right? Similarly, in our applications we're going to focus on, the database system is going to be doing the same set of operations repeatedly over and over and over again. Right? So if you remember back from our American Idol example, when someone calls in, there's only one transaction that's ever going to be invoked, and that one transaction only has 3 steps. So we're not going to focus on optimizing the system to allow people to write arbitrary transactions or open up a terminal and write a random query in. And the last thing is that both of these items are very small or have a small footprint. So what I mean by that is greyhounds actually have a small footprint or paw print for a dog of their size or stature. And similarly, our transactions are going to have a small footprint in the overall database. So the data set itself could be quite large, but each individual transaction is only going to touch a small number of records at a time. So we're not talking about long-running queries that are doing full table scans, doing complex joins to compute aggregates and things like that. We're really talking about transactions that come in, use an index to find to do point queries to find individual records that it wants to read, and only processing them. So now, based on these 3 properties, we've designed a system called HStore that's optimized from the ground up to be specifically to operate efficiently for transactions in these types of applications. So this is work that I've done as part of my dissertation, along with colleagues at Brown, MIT, Yale, and what was at the time Vertica Systems. And so in HStore, and this maybe get to address some of your questions, in HStore there's 3 key design decisions that we're going to make that are a direct reaction to the bottlenecks that we saw in the traditional systems. So in the traditional systems, they're inherently disk-oriented. Right? So all that machinery that I talked about before in that pie chart, a lot of that is based, you have to have because everything, a transaction could try to touch data that's not in the buffer pool, but that's on disk. But for these modern workloads that we're looking at, in many cases, the database can fit entirely in main memory. You can buy a few number of machines that have enough RAM that is able to store the entire database entirely in main memory. And so in HStore, we're going to have a main memory storage engine. We're going to assume that the database is small enough to be able to fit in RAM. So we're talking about databases that are usually, for these type of applications, are about a couple hundred of gigabytes. And the largest one that I know of is Zynga, which is roughly about 10 terabytes. So again, it's perfectly feasible to buy enough machines that have enough memory to do this. The second thing is because in the traditional systems, because there's a disk, they have to allow transactions to run concurrently, because at any time one could stall because they're trying to touch something that's not in the buffer pool. And so to do this, you have to have a concurrency control scheme that's using locks and latches and mutexes and other synchronization methods to make sure that one running transaction does not violate the consistent view of another transaction that's running at the same time. But now if everything's in main memory, you're never going to have those kind of disk stalls, right? So it maybe does not make sense to actually have a lock manager and have concurrent transactions anymore. So in HStore, we're going to have serial execution of transactions, meaning we're going to execute transactions one at a time at a single core. And this sort of makes sense because if the cost of acquiring a lock in main memory is the same as actually just accessing the data in main memory, you might as well go access the data. And then lastly, in a traditional system, they have to use a more heavyweight recovery mechanism to make sure that all changes are persistent and durable after a crash. And so they have to use something where they record the individual changes that were made on each record that was read or written to by a transaction. So in HStore, we're going to use a more compact logging scheme that's more lightweight and more efficient, where we only need to store what a transaction was rather than what it actually did. And I'll explain a little bit more about that in a second. So now, the basic architecture of HStore is that the database is going to be split up into disjoint subsets called partitions that are stored entirely in main memory. So in this example here, I have a single node. I'm going to have 2 partitions. And so my database is going to be split into disjoint subsets where one half of the database will be in one partition, the other half will be in the other partition. Now, for each of these partitions, it's going to be assigned a single-threaded execution engine that has exclusive access to all the data at that partition. And what that means, if any transaction needs to touch data at that partition, it has to first get queued up and then wait to be executed by that partition's engine. And because we're going to have these granular locks at the partition level, when a transaction is running, since the engine is single-threaded, it knows that no other transaction is running at the same time, so we don't have to set any fine-grained locks or latches down within the underlying data structures within the partition. So what it is to run beginning to the end without ever stalling. So now to execute a transaction, the application comes along, and it's going to pass in the name of the store procedure that it wants to invoke, and then the input parameters for that transaction. So in HStore, the primary execution API is going to be through store procedures. And store procedures are essentially, in our world, a Java class file where you have a bunch of predefined queries that each have a unique name. And then a run method, it takes in the input parameters sent in by the application and invokes program logic that will make invocations of the predefined queries. And so we have a very important constraint in our store procedures in HStore, and that is they have to be deterministic. And what I mean by that is they're not allowed to use a random number generator inside the run method, or go grab the current time, or make an invocation using RPC to some outside system. And all the information that it needs to process that transaction has to be contained within and passed in from the client. And this will be important later on for recovery mechanisms. Yes?
Does that mean you can't depend upon this prior state of the database? You can't have conditional logic, which...
No, that's OK. Yeah. So the determinism really has to be if we re-execute this transaction at a later date in the same order that we processed it originally, we need to end up with the same ending state. It's perfectly fine to do a query, read back the state, and then if branch do something different. That's fine. OK, so now the transaction request will get queued up at the partition that has the data that it needs. And once it reaches the front of that engine's queue, it'll have the global lock for that partition, and it's going to be allowed to start running. Now, when it finishes, we're going to go commit its changes right away. But before we send the result back to the application, we have to write out the same information that the application sent us originally out to a command log on disk. Yes?
Does this mean that an individual transaction can't access multiple data from multiple partitions?
No, it can, and we'll get to that too. That's later. Yes. And so this, I'll say too, this command log is done, this writing this out is done as a separate thread, so we're not blocking the main engine. Yes?
Does this mean that as you scale up in cores, you have to do finer grained partitioning?
Yeah, so yeah, you could. I mean, for one core, there's one partition. I mean, finer grained in the sense of like...
You have more cores, you have more partitions.
Oh, absolutely, yes. And so, there is an upper limit, and that's sort of related to his question. There's an upper limit as you partition more, you could end up with more multi-partition or distributed transactions. Yeah. Yes. And so we're going to batch these entries in the command log together and do a group commit where it's just one fsync to write them out all at the same time. And so we're advertising the cost of doing that write across multiple transactions. So now, once we know it's safely written and durable out to the command log, it's safe for us to go ahead and send back the result to the application. Now, there's also a replication scheme that's going on here. We're doing active-active replication, where we just can forward these transaction requests from the application to our replica nodes, and they'll process them in parallel. But I'm not going to talk about that today or right now because it sort of complicates everything we'll talk about later on. But if you want to know more about it, I'd be happy to talk about it afterwards. So now, while this is all going on, the database system in the background is taking asynchronous snapshots of the partitions in memory and then writing them out to disk as well. All right, so we're going to use a copy on write mechanism so we don't slow down the main execution pipeline of the execution engines. And so now if there's a crash, all we need to do is load in the last checkpoint that we took, and then we can replay the command log to put us back into the same database state. Again, so this is why it has to be deterministic. On recovery, we want to make sure we end up with the same result.
You need a transaction consistent checkpoint, right?
Yeah, correct, yes. But you need to make sure all the nodes are doing the checkpoint at the same time, but then you can use a copy on write mechanism to make sure that you don't block everybody else. But yes. OK, so now if we go back to our Japanese American Idol workload we looked at before. And this time, we're going to run the same workload on the same hardware using HStore. We can see when we give HStore a single CPU core to process transactions, it can do over 20,000 transactions a second. But now the main difference is as we scale up the number of cores that we give the system, we can get better and better performance, up to about factor 25x over what we can get in the traditional systems on 8 cores. And so now immediately every single one of you here, when you see a performance gain like this, should have a red light or siren going off in the back of your head telling you to be skeptical. And what I'll say is that this is not a parlor trick. Right? All 3 systems are running the same workload, the same serializable isolation level, and they're running with the same durability and persistence guarantees. So if the database crashes, all 3 systems can recover any transactions that were committed. So we can actually look at some other workloads and see the same kind of performance results. So TPCC, as everyone I'm sure is aware of, it's the canonical benchmark that everyone uses to measure the performance of these types of systems. And we see the same kind of performance result. As we get more cores to HStore, we can get better performance, whereas the traditional database systems is simply flatlined. Telecom 1 or TM1, or it's actually referred to as TTP now, is a workload from Ericsson where that simulates someone driving down the highway with their cell phone, and the cell phone has to update the towers and say, if you need to call me, here's where to find me. And we see the same kind of result as well. As we get more cores to HStore, we can do better, whereas the traditional systems, the performance actually gets worse. So now you would look at these results and say, well, this is great. HStore does much better than a traditional system. Why would I ever want to use a traditional system today when something like the architecture of a main memory architecture like HStore can get much better performance? And the answer should be quite obvious to everyone here, and that is it's an inherent problem to a main memory database system is that you're limited to databases that can fit in main memory. But that's OK, because out of the box, HStore supports multi-node deployments. So here, if we look at the same 3 workloads that we started off with before, and this time, we're going to scale up the number of nodes in our cluster. So we're going to go from 1 to 2 to 4 nodes with 8 cores per node. And we see the same kind of thing. As we add more hardware to the system, we're able to get better performance. And this checkered line here is sort of marking where we want to be in terms of achieving linear scalability, which is the gold mark standard what you want to have in a distributed database. So as we double the number of nodes, we want to get double the performance. In the case of the voter benchmark, we're pretty close to achieving that. In case of TPCC and Telecom 1, we're a little bit off because of the nature of the workload. So again, now you look at this and say, well, this is great because in HStore, I can add more machines. I can support databases that are larger than memory on a single machine. Why would I ever want to use a traditional database system when I can just buy more machines and scale out with HStore? And again, sort of related to the gentleman's here's question is, in these 3 workloads, all the transactions were single partitioned, meaning
not CPU cores is number of machines?
It's CPU cores and divide by 8. So it's 1 to 2 to 4. Yeah, I should have marked that. Sorry. So for these workloads here, all the transactions only need to touch data at a single partition. So when they ran, they did not need to coordinate or synchronize with any other node in the cluster, and that's why we're able to get this really good performance. But now if you have a transaction that has to touch multiple partitions, you end up with what is known as a distributed transaction. And this has really been the main bottleneck, the main problem of why a lot of the distributed databases from the 1980s did not really come popular, because this is why these systems aren't able to scale up. And although HStore is a NewSQL system, it's a modern code base and modern hardware assumptions, we're not immune to this problem either. So now if we go back to the TPCC benchmark again, and this time we make 10% of the transactions be distributed, meaning 10% of the transactions need to touch data at 2 or more partitions. Now we see as we scale up the number of nodes, the performance is terrible. It's completely flatlined. And we're nowhere near where we want to be in terms of linear scalability. So now you look at this and say, this is god-awful. Why would everyone want to use HStore? Because if I try to scale up and support and have multiple nodes in my cluster, I'm paying for more hardware, I'm paying for more energy, I'm paying for more maintenance for those machines, and I'm not getting better performance at all. I might as well go back to a traditional database system where at least if I pay more money, I can try to scale up and get better hardware that way. And so, this is a real problem, because not all workloads can be perfectly single partitioned in the way that we assumed before. So in the early days of this project, we actually visited PayPal, and PayPal had this legal requirement where customers from different countries couldn't be on the same partitions. So if you had an account in Italy, if you had an account in the US, you want to send money between the 2 people, they had some legal requirement that says that had to be a distributed transaction. So an architecture like HStore simply wouldn't work for them. And in many cases, the application schema itself is not easily partitionable at all either. And so you end up with this bottleneck. So this is the main thing we're trying to solve here. How can we try to achieve linear scalability? And when we have distributed transactions. So to do this, the first thing we have to do is we have to figure out, well, what's going on? What is it about these distributed transactions in a system like HStore that's causing this bottleneck? So now if we want to look at an example where we have a multi-node cluster, say we have an application that comes along and it submits a transaction request to the system. And this time, this transaction needs to touch data at these 4 partitions. So the way HStore's concurrency control protocol works is that we have to acquire the locks for these partitions first before the transaction is allowed to start running. And the reason why we have to do it first is we don't want to have to do deadlock detection if we have sort of more fine-grained locking, and because that would be expensive to do in a distributed environment, especially when we have transactions that are finishing on the order of milliseconds. But now the first problem we're going to hit is we don't actually know what partitions this transaction actually needs before it starts running, so we have to lock the entire cluster, even though we're never going to need most of those guys. So now once we do this and the transaction is allowed to start running, it can issue the query requests to these remote partitions to either access or modify data that's located at the other nodes. And we're going to see a second problem. And that is, if we actually knew the number of queries that this transaction needed to execute at each node, we would see that it needs to execute more data at this node at the bottom, or touch more data at the node at the bottom. So what we really wanted to do was when the request came in, we wanted to be able to automatically redirect it to this node down here and run the stored procedure there, because that would result in a fewer number of network messages, because most of the data was going to need to be local. We wouldn't have to go to the network to send query requests to these remote nodes. But again, we don't know this information because we're dealing with arbitrary stored procedures. Right? So this is a difficult problem, and you could try to apply things like static code analysis and other things, but that would be too slow to do in every single transaction that comes in. So luckily for us, the solution to this problem can actually be found back at the dog track. So I wouldn't say that I was going all the time. I wouldn't go every day, but you go a couple times a week, holidays, 4th of July, Memorial Day, Mother's Day, stuff like that. And it was one of those things where you start going to the same place over and over again. You start to notice the same people and the same patterns, right? Of people doing the same thing every single time. And I met this guy named Fatface Rick, and he first came to my attention because he was winning every single bet he was making with all the bookies at the track. Right? He wasn't betting a lot amount each time, but every single time he made a bet, he was right almost 100% of the time. And it took me a while, but I finally figured out what he was doing. Every single morning before a race, he would go down to the parking lot where all the trainers would bring in their dogs and sort of check in for that night's race. And he would pretend to be a vet from the State Gaming Commission. And he would tell the trainers, I need to look at your dogs and make sure that they're up to regulation and they don't have any health code problems, right? But what he was really doing was checking them out to figure out which ones were in the best shape, which ones were the strongest, and which ones didn't have any injuries. And those are the ones he would go make his bets on. And that's why he was always winning. So this is the same thing we need to do in our database system. We need to know what things are going to do when they come in before they start running. So to do this, we've built a machine learning framework called Houdini that we've integrated into HStore that's going to allow us to predict behavior of transactions right when the request comes in without having to run it first. And so we have a very important constraint in this work of how we make these predictions, and that is we can't spend a lot of time figuring these things out. Right? So we can't spend about 100 milliseconds figuring out what a transaction is going to do if that transaction is only going to run for 5 milliseconds. So the underlying component of how Houdini works is that we're going to create Markov models or probabilistic models for all the stored procedures that the application could execute. And so we're going to build these based on from training sets of previously executed transactions. So for each model, we're going to have the starting and terminal states for the transaction, so the begin, the commit, and the abort states. And then we're going to have the various execution states that the transaction could be in at runtime. So these execution states are represented by the name of the query being executed, how many times you've executed the query in the past, and what partitions this query is going to touch. Now each of these states are going to be connected together by edges that are weighted by the probability that if a transaction is at one state, it'll transition to another state. So now at runtime, when a request comes in, Houdini will grab the right model for that unique request, a unique transaction invocation, and it'll estimate some path through this model. And based on the states that the transaction will visit when it traverses through the model, that'll tell us what are the optimizations we can apply at runtime. Now, if we get our predictions wrong, it's OK, because at runtime, we're actually going to follow along with what state transitions the transaction actually does make. And so we're maintaining internal counters of how many times it goes across some path. So we start noting that our predictions are deviating from what we see in reality or in the actual runtime behavior of transactions. we can just recompute these edge weights really quickly online, and it's a cheap computation to get us back now in sync what the application is actually doing. So how we're going to generate these models is that we're going to have a training set of previously executed transactions. Yes?
So I can understand why you predict commits to be more frequent to the boards. But it seems to me what you really need to do is be able to predict which partition's being referenced.
Okay, so again, that's what we do. So the state has the name of the query being executed, how many times it's executed the query in the past, what partitions this invocation of that query will go to. And then because it's a Markov model, we have to encode all the history at each state. We also have the history of all the partitions we've touched in the past.
So your weightings there suggest sort of an overwhelming path to choose, but you could easily end up with a path in which there are 3 possible partitions and they're each around 33%? Or
yes. Give me like 2 minutes and I'll solve your problem. Okay, great. Great segue. All right, so we have a training set of previously executed transactions, right? And so these are all the queries and input parameters that were invoked in each transaction. And we're going to feed that first into a feature cluster that's going to split them up based on characteristics or attributes of the transaction's input parameters that create the most accurate models. So these could be things like the length of an array parameter, the hash value of another parameter. And now with these bucketed training sets, we're going to first feed that into our model generator that'll create the Markov models for each bucket. And then we'll have a decision tree, the classifier to create a decision tree that'll split them up based on the features that we originally clustered them on. So now, one of the features could be what's the hash value of some parameter, and that'll tell us what partition we're going to execute this query on, or what partition we're going to execute this transaction on. And that'll tell us now that it almost becomes like a linear state machine where we don't have that equal probability of what partition we could take because it's no longer a giant monolithic model. It's more individualized. Yes?
There are many models, many classifiers that you could have used.
Yes.
Why did you choose a decision tree?
So we chose the decision tree because we want to be able to quickly traverse it and say at runtime.
Runtime speed.
Yeah, correct. So this whole top part here is actually what I was going to say next. The whole top part here we're doing offline.
Yeah.
So it can take a while. That's fine.
Right.
But now at runtime, we can quickly traverse the decision tree and then quickly estimate some path to the model. So we can do this bottom part here in microseconds per transaction.
Just to make sure I understood, so the parameter value is being passed in.
Yes.
From that, you can exactly know. There's in fact no prediction because you exactly know which partition that transaction is going to touch, or you don't.
It tells us it suggests to us what partition to run the stored procedure at. But now within that stored procedure, it could touch any number of partitions. It just so happens in the case,
Then how does it help you with the locking? So let's say, let's take a concrete example.
Yes.
So let's say the predicate is name equal to question mark.
Yes.
And let's say we have name equal to Andy.
Yes.
How do you know which partitions to lock?
If I'll sort of jump ahead for this. Right. So when a request comes in, we grab the right model, do a little hand wavy magic, which is really machine learning. So we take the model that's best representative based on the decision tree, and then we estimate what the path is through it. And so when we're trying to figure out what the state transitions we're making, since we know what the tables are partitioned on, because we have to be told that ahead of time, now we know what the input parameters are to that transaction, and that can tell us what actually partition the query is going to have to touch. Yes?
There could be some dependencies here that are actually stored in the database. So
Correct.
let's say I look up my main customer and the hash of my main customer now determines the partition.
Yes.
What is your logic? So in many cases this should work fine.
Notice if you have to read the state of the database and say based on that, now you hash whatever that the output of one query is being used as input for another query. These models don't encapsulate that information. Right? So we take care of that in other ways. So we take care of that, again, for the partitioning work we've done, the automatic database design work we've done. We can figure out, hey, we see this pattern happen a lot. It's usually read-only, read-mostly. So we'll create secondary indexes that are replicated at every single node so that we can do that lookup, and then that'll direct us to the right location. So there's other things more than that. Right?
But you would know, right, sort of in these cases, do you have any mode of saying, well, for these transactions we get a very accurate model, for these cases, we just don't know. So we'll back off from our prediction and use something more conservative, because even though your most likely path may not be very likely.
Yes. So your question is there a way for us to identify what are the different types of workloads that we see that have this dependency where you're reading stuff from the database system, and then maybe not apply these optimizations for them?
Or just more general, do you know when your model works well and when it doesn't?
We have not done anything formal about that, but I can tell you sort of off the cuff things. Again, doing that lookup, and then using output of a query as an input of another query, that won't work well with this. But again, we take care of that in other cases. If you have sort of large range queries that have to touch multiple partitions, and it's arbitrary what partitions you have to touch, that won't work well in this. But I'll say for those types of workloads, for that second type of query, we don't see often for the type of applications we're focusing on. That's more getting to like the real-time analytical stuff, which we haven't focused on yet. And I'll talk about that in future work. Any other questions? Yes.
So are you going to do optimizations for locking the partitions as well, based on your predictions on which partitions the transaction is going to access?
So we can do, like this case here, we have our path, right? So we know what partitions we think it's going to touch. So now we'll only lock the ones we need.
And what if the prediction model is incorrect, and somewhere during the runtime you decide now you have to lock one of the other?
Right. So yeah, a lot of segues here. Right. So if we predict that if we fail to predict that we need a partition in the beginning and we don't lock it, when the transaction tries to actually access that partition, we abort it, roll back any changes, and restart it and acquire the locks.
Just to prevent any deadlocks.
Correct. Absolutely. Yeah. You can't touch anything without having a lock beforehand.
So the cost of a misprediction is just the transaction aborts and restarts with the better estimate.
No, so there's other things as well. So like you could try to lock something you don't actually end up needing, and then now the thing is just sitting idle and can't do anything. I don't have a good sense of what's worse.
Okay.
I know that, I guess I'll just jump to it now.
And my question is,
yes.
How big is the difference, so if I remember correctly from our previous conversation,
yes.
the difference between a transaction that runs correctly, is predicted correctly, runs
yes.
either completely local or on a few transactions, versus a transaction that needs to run locking everything? The gap between these is huge, right?
Yeah. So yeah.
But the idea of running a transaction and aborting halfway to then rerun the very slow one, the overhead of that abort is actually not, if I understand correctly, is not that relevant. Is that a fair statement?
The overhead of aborting the transaction and restarting it.
Yeah. So I tried to run the fast version of it.
Yeah.
I fail. I mispredict.
Yes.
And I run the slow version.
Yes.
The try to run it.
When you say slow version, it's more like you restart it and you lock. You're still not locking the full cluster. If you have to lock the full cluster, so this is the naive prediction scheme. This is when you assume that everything's single partition, and then if you get it wrong, you abort it, restart, and acquire the locks that you need, right? And then the top line is when we actually use Houdini, when we're accurately predicting what we actually needed. And so it's about a 2x difference between the two, right? I thought sort of asking, I don't know whether it's better to lock something that you don't end up needing or miss the lock. My sense is it's roughly the same, but if you have to lock the entire cluster every single time, the performance is absolutely terrible, right? So this is what we can do if we use our model. Sorry, yes?
So this model, how would it compare to, say, doing just a dirty run of the transaction that didn't acquire any lock?
To simulate it, yeah.
Use that as a model,
All right, so there's other techniques that you could use. Like you could simulate the transaction, you could use static code analysis, you could use chain checking. For the simulating one, I think the overhead of doing it might be. The problem with that is you miss things like if I read back a value and do an if branch.
But the statement here is that the fast version, the fast version is much faster than the slow version.
Yes.
You could do an even faster fast version which didn't acquire locks just to see where you think it might touch.
But you still have to acquire the locks. Are you suggesting you just simulate the transaction, not in the engine, in a separate thread, see what data it tries to touch,
right. Totally
then that
reads.
And that tells us how to schedule
incorrect.
it. Yeah.
Being everything memory, you almost have the same cost of actually executing a transaction, right?
I thought acquiring the locks is a big delay, though. Like you have to.
So you would, like, for your case, you would still have to acquire the locks.
No, like I'm saying, like when you do the dirty simulation, you acquire no locks. So yeah, you do some I/O, but.
So you're sort of like doing optimistic concurrency control kind of thing.
Not even. If you try to run a transaction
Yes.
on a separate thread,
Yes.
not touching the real data, pretending that there's not
Right.
the only transaction exists in the world.
And that'll tell you what partitions you need to lock. But now when you run it for real, you have to do the concurrency control scheme with acquire the real locks.
That's
and
right, but I'm just wondering, like this dirty simulation is also a model of what
Correct,
needs
yes.
to be locked.
Yes.
And then how, so you have, it's
So-
sort of like a fancy machine learned static analysis.
So there's other.
So I'm just wondering, what's the straw man, I guess is what I'm trying to get at. Like, how should I think of this model as being better or worse than other attempts to guess at what to lock?
Right, I got that. So I have not done that simulation example. That is something I have to do for my dissertation work. There's other things that we can do with these models that I'm not really talking about today. So we can do things like we can identify when we're done with a partition. So we can go ahead and send like the early two-phase commit message. We can also I don't want to bring it up because Phil's here, but you can do things like if you know there's never going to be a user abort with absolute certainty, maybe you don't need your undo locks, undo logging, and you can get about a 10% speed up as well. But I don't have a good answer of how much you can get just using simulation. There's other things I'll talk about later on, how we can leverage these models and to do speculative execution and other things like that, where we can talk about afterwards whether we can still do simulation for that. But it's more, we're doing more than just figuring out where should we send it and what should we lock. And that's my hunch of why just doing a quick and dirty simulation might be insufficient. Any other questions? Okay, so this is what we get about 2x improvement over that naive prediction scheme. But we can compare how well we can do versus what I'll call the optimal case. So this is if you have an oracle that knew exactly what every single transaction was going to do. This is the best performance that you can get. So we're about 98, 99% accurate. Right? So there's some cases where we maybe lock something we didn't end up using, or we lock something, or we don't lock something we do up need later on. And so we're not that far off from where we want to be in that case. And actually, if we run this even longer over time, we can learn more and our models get improved and get closer and closer. But so now 2x improvement is always a welcome.
Sorry, when you say optimal, you mean you have perfect prediction?
Yeah, absolutely. Yeah, so I hard-coded something in the system that said, here's a request. What is it going to do?
I'm still sort of failing to see why, how these models can be so accurate. So what's the intuition? So let me go back to the example I had before. Let's say there are a lot of transactions where name equal to Andy kept coming.
Yes.
So you have a history of that
Yes.
parameter value showing up, that specific value, right?
No, it's more like.
But imagine for a second
Yes.
that you see a parameter value you've never seen before.
Yes.
How well does the model do in those cases?
So we're doing.
In OLTP workload, I would imagine there would be a very long tail of parameters
Right. So again,
that you've never seen before, even though the stored procedure is exactly the same.
yes, correct. So we are. This is like. Let me hold your question, and then I'll have a slide later on that'll show you. Because again, we're doing hash partitioning. We don't have to encode. Here's Andy. Here's Vivek. Here, individual records of how to map them partitions.
Probably learning based on the result of applying the hash function.
Correct. Yes. Yes. But I'll show how we can be more deterministic in our selection later on. Okay. So 2x improvement is always pretty good. It's always a welcome improvement when you're doing database research. But the problem is, if we change the graph to be reflecting where we want to be in terms of linear scalability, we're still not in the right direction. So the absolute numbers have improved, but the trend is still not where we want to be. So this doesn't help us. So again, we're adding more machines, and we're not getting the better performance that we want. So the question is, what's going on? What's causing us not to be able to scale up? So it has to do with the inherent nature of our concurrency control model. Right? And that is, because we have these granular locks at a partition, when a transaction starts running, when a distributed transaction is running and it holds the lock at remote nodes, these remote nodes, the engine for them, are idle, doing nothing, because they have to wait until the distributed transaction sends a message over the network to tell it to execute a query and send back the result, or start the two-phase commit process to finish the transaction. So they're essentially doing nothing. So now, once the stored procedure does send a request to these remote nodes, they have something to do. They can process the query. But now we go back, we sort of flip, and now the guy at the bottom, he's idle because he has to wait for the results to come back before he can make forward progress. And once it does come back, again, the remote guys go back to being idle. Right? And this is because we're optimizing our system for these single partition transactions, which are the majority of the workloads that we're looking at for these types of applications. But because we have these such granular locks and we have these long wait times, this is why our system is just being completely slowed down. So once again, one last time, the answer to how to solve this problem can be found back at the dog track. So I first met these guys. They were ex-taxi drivers from Argentina, and they were kind of like a seedy group. They didn't really talk to anybody else. They were always talking amongst themselves. And I first noticed them because they were always running around looking very, very busy. So most people go to the dog track to relax. At least that's what I do. And because there's actually not a lot of things to do while you're at the track. Because there's only about 14 to 15 races per night. And each race is about 50 seconds. It's over pretty quickly. So there's a lot of time you're just sort of sitting, eating food, waiting for the next thing to happen. But these guys weren't here to relax. They were at the track to make money. And so what they would do is they would go down to the payphones by the bathrooms. And whenever we were in between a race at the track we were at, they would go call their bookies at tracks in the next county over so they can make more bets and so they can make more money. So again, they're doing something useful when everyone else is sitting around idle. So this is the same thing we want to do in our database system. We want to be able to do some kind of useful work whenever we know that an engine is blocked waiting on the network. So to do this, we developed a new protocol that allows us to speculatively execute single partition transactions at an execution engine for a partition that is blocked because of a distributed transaction. And the key thing about this is that we have to make sure that we maintain the serializability of the database system. So my apologies, Phil, you have to sit through this. So for a serializable database, what we want to do is we want to have the end state of the database to be the same as if we execute transactions sequentially one after another. And this is essentially what we're doing now. Right? So we have a distributed transaction and two single partition transactions. And each of those single partition transactions do not start executing until it knows that its previous guy has committed successfully. But we see, in the case of the distributed transaction, we have this huge block of time here where we're idle, where we're waiting for somebody to come over the network to tell us to do work, or waiting for the result to come back before we can continue forward in our transaction. So what we're going to try to do here, we're going to try to find a schedule where we can interleave these single partition transactions during this time when we're blocked, and then we're going to hold on the results until the end, and we're going to do at the verification process to check whether everyone didn't create any conflicts, and that the end database is still the same as it was if we executed them sequentially, and so that and then that we have a consistent view at all times. So this sort of looks like optimistic concurrency control, right? But in that original paper from Professor Kung in 1981, they assume that conflicts are very rare. So that the number of transactions you have to abort because in the verification step, because there's a conflict, is small. But in a lot of the applications that we've looked at, there usually is a lot of skew, either temporal skew or popularity skew. So conflicts are not rare, and you end up having to abort a lot of things over and over. So what we're going to do instead is we're going to use pre-computed rules that allow us to identify whether two transactions conflict, and then if they don't, we know that it's safe to interleave them. And then now at the verification step, because we scheduled them based on the predictions that we generate from our Markov models, if we know we selected them that they wouldn't conflict, as long as they did what we thought they were going to do, we know there aren't any conflicts and we can commit everybody all at the end safely. So now let's look at an example here. So let's say we have a distributed transaction that needs such data at these two partitions. So the store procedure is going to run at the top and acquires the lock for the partition at the bottom. So when it starts running, at some point it's going to issue a query request to this partition at the bottom. And then that means that the store procedure will get blocked and is idle because it has to wait for the result to come back. So now when this occurs, Hermes will kick in, and it's going to look at this engine's transaction queue to try to find single partition transactions that it can interleave. And so we have two important requirements of how we're going to do this scheduling. The first is that we have to make sure that the single partition transactions will finish in time before the distributed transaction needs to resume. So we've extended our models that we used in Houdini to now include the estimated runtime in between state transitions. So because you want to call it like cascading stalls, because you're holding these locks, you want to be able to finish up and have everything commit as soon as possible. So let's say we have a distributed transaction. We have the prediction that we generated from the model in the beginning. And so it just executed this query here. And we anticipated that it's going to execute this next query here. So now our models include the estimated elapsed time in between these transitions at this partition. So now when we go look in our queue to try to figure out what guy we want to execute, we want to make sure that they'll finish within this time. But then the second requirement is that we need to make sure that we don't have any read-write or write-write conflicts. All right, so let's say for this speculation candidate, if we scheduled it, we have this problem where the distributed transaction just read the value of this record X from the database at this partition. And then it gets blocked because it has to wait to execute some query at a remote node. But now if we execute this candidate here, it's going to write some value that's going to change the value of that record X, the same one that the distributed transaction read. So normally this would be OK, except that when the distributed transaction resumes, it's going to try to read that value back again. And this is going to be a phantom read. It's going to get an inconsistent result. So this is a conflict that we can't allow to occur. So we're not going to choose to speculatively execute this guy, and we're going to skip it and go down to the next one. This next guy will finish in time, and it doesn't have any conflicts, so we know it's safe to execute. So we're going to pull out of the queue and execute it directly on top of the distributed transaction at that partition, as if it had gone through the normal locking process.
Can you prove that this will never ever going to have any conflict, or you're saying it's very unlikely and I will abort if he goes away?
So I'm not claiming that we can do this for all store procedures. For some things, it's too complex then to try to figure it out. But for some basic things, like I read table X or table foo, and this guy reads and writes tables bar, I know there's no conflict, so it's OK to do that.
So you're OK.
It's rules like that. Yeah, heuristics.
Okay. But so my question is, so imagine there are two versions of these you can imagine.
Yes.
One is like, it's absolutely guaranteed by construction of these two transactions they will not interfere.
Yes.
So I'm game to do it, and I potentially cannot even check afterwards what happened because.
No, so we still can. We'll check at the end at the logical level, and if there is a conflict that occurs, we can abort and roll back. So we're not going to be unrecoverable.
And the other case is I might have a conflict, but there's a 0.001% probability to do it. You can go ahead anyway and abort if needed?
Yes.
Okay.
Yeah. And so it's actually sort of related to his question is, right? So when it finishes, we'll commit it, but we won't commit it right away. We'll put its results on a side buffer because we need to wait to learn whether the distributed transaction finishes. Yes.
So maybe I'm missing something, but if you know there's no conflicts, then you could commit the single partition ones right away, couldn't you?
But the single partition transaction could have read something written by the distributed transaction, and therefore you have to hold it because you can't release some value.
The conflict.
It's not a conflict in the sense of like I read something and then I try to read it twice and I don't get a back to a result. It's more like you don't want to release the state of the database of any changes for the distributed transaction until you know the distributed transaction has committed successfully. For some cases, yes. If you read something that the distributed transaction hasn't touched, then it's OK to send back the result. Yeah.
So the problem is that if I read something, the distributed transaction.
Depends on how finely you look at it.
Correct. Yes.
Yeah.
And it depends on whether the distributed transaction has written anything before it got stalled. Right? If it just reads something, then it's OK. I'm just sort of giving an example of like when you would have a read-write or write-write conflict. So normally, and this is sort of related to Vivek's question in the beginning, normally this would be an unsafe thing to do because if you're using these probabilistic models, there's a bit of randomness involved in picking what path you're going to take and trying to identify what data you're going to, the transaction is going to end up reading and writing. But we can actually exploit a property of our stored procedures to make these selections or predictions more deterministic. So let's say we have our transaction. A new transaction comes in the system, and it starts off at the begin state. And again, we want to figure out what path we're going to take through this model. And that's going to be able to tell us what data we're going to read and write. So normally, you would say, all right, well, here's the two transitions I can make from where I'm at now. So I have to roll the dice, and based on the edge weights, the distribution of the edge weights, you'll make go down one path or another. But in this case here, we see that there's only one query that the transaction could ever execute, this get warehouse query. And so in the get warehouse query, we see that there's an input parameter that's being passed in from the program logic of the store procedure that's going to be used on the warehouse ID, which is the primary key for this table. And so since we partitioned this table on this warehouse ID, that tells us if we know the value of this input parameter, that tells us exactly what record we're going to access. And so we can generate a statistical mapping between the input parameters that are passed in from the application into the transaction to the input parameters of the queries. So that means if we know that, since we know the value of the transaction's input parameters, we know the value for this input parameter for the query. So that tells us exactly what path we're going to take, what transition we're going to take for this case here, and we can continue and do this all down the line. So again, I'm not claiming that we can do this for all store procedures, but for a lot of them in the applications we look at, we see this pattern and we can exploit this.
Is this analysis done manually, or you have an automated technique?
It's automatic, yeah.
Okay. So it's what is the intuition for this? Like, given an arbitrary program, how do you go about? So now you had a semantic knowledge that warehouse ID is.
Yes.
You have a semantics associated with warehouse ID, but given an arbitrary application, how do you?
So we have these store procedures. We have these workload traces. We say there's a bunch of different ways you could do this. We'd end up with the same result. The static code analysis can tell you to do this. Taint checking is another example of how to do this, right? We do a dynamic approach where we take these previously executed workload traces and we say, all right, well, this input parameter, we see the value of this query being executed within this transaction. How often does it correspond to the input parameters for the store procedure? Okay. And so if we see that there's a direct mapping, then we know that we can identify this. Okay, so now this makes our predictions more accurate, more deterministic. So now at runtime, when we want to commit a bunch of speculative transactions, instead of checking the read-write sets and the dependency graphs in between them, we just need to verify that all our transactions at the logical level made this correct path transitions that we predicted they were going to. And because we have our pre-computed rules to schedule them to not conflict, and those rules are based on our initial predictions, as long as our predictions are accurate, we know that there's no conflicts and we go commit everybody all at once and we're happy.
Can you give us an idea of what's the size of this set of rules? I mean, for every transaction type in TPCC, how many different rules can come out? And, like how big is this space of things you have pre-computed?
Yeah, I don't have a number.
No, but it's like in the tens, in the thousands, in the millions.
In the hundreds. In case of TPCC, in the low hundreds. Yeah.
The other question that I have is, okay, so TPCC is a benchmark.
Yes.
There are some assumptions, in this work that may make sense in TPCC, and I just don't know if they make sense for the types of applications that require, this sort of scaled out, lightweight transactions.
So I would say, TPCC is actually very representative.
Is it?
Yes.
So you do typically have those kinds of conflicts and things like that?
Yes, in TPCC, the workload, in both terms of the complexity and what the transactions actually do, is actually very representative of what I've seen in the industry.
I have to confess, I'm a little bit surprised because it seems to me like if I'm thinking about, Amazon shopping baskets or something like that, then it doesn't seem to me like there's likely to be a lot of conflicts, because you'd have to have, conflicts within the same shopping basket, and that doesn't seem likely to me. There may be shopping baskets that are hot, but
yes,
not necessarily transactions that are going to conflict with each other over those shopping baskets.
Shopping basket is a bad example because they don't actually use transactions for that. I don't have I can't give you a number to say like 80% of the workloads we see have these properties, but I would say in the things that I've looked at, it's fairly common. But I don't have a way to quantify that just yet.
Well, partly that's self-selection because those are the only workloads that really work well on this particular system. So.
Right. So again, I'm not trying to build a general purpose system. I'm very careful about saying that. Right. So yes, there could be some things that clearly you would not want to use HStore for, and because they don't have these properties. But I would say that there are a significant number of them. So, all right.
With the interaction with VoltDB, you get the impression that this research would apply to their customers?
Yes. We'll get to that. Okay, so let's go back to the TPCC benchmark a third time. Again, we're going to have the same number of distributed transactions as before, and we're going to scale up the number of machines. And this time, when we use HStore using Hermes, you can see that we can get almost about 60,000 transactions a second across 4 machines with 8 cores apiece, right? And so now we see in terms of linear scalability, we're in the right direction. So we're not actually going to be, we're never going to be perfectly linear scalable because we're a bit conservative in our estimates. There could have been cases where we could have executed a transaction, but we didn't because we didn't want to cause these stalls. Yes?
Before on a previous slide, you showed us TPCC, and you said something like 10% distributed transactions. So, what's the fraction of distributed versus single partition here? And then if I change that, what happens to this?
Yeah, absolutely right. So they're all executing the same number, absolute number of distributed transactions. The percentage varies because what we're doing is we're executing more single partition transactions. You absolutely is an astute observation. We're not actually doing anything to make each individual distributed transaction run faster. We're just sort of be able to do more work when we otherwise would be idle. It's future work to be able to speed up, each individual distributed transaction and reduce its latency.
Right. So specifically, you're able to speculatively execute the single partition transaction.
Yes.
So what fraction of the transactions here are single partition? I guess I'm just wondering, because it seems like you need to have basically a nice queue of single transaction or single partition work that's ready to
Correct,
go
yeah.
in order to exploit this.
Yes.
So
Yes.
is that typical, and is that a dial you can turn here to show me what happens to the slope?
Yeah, so again, if you add more distributed transactions, yes, you're going to be down here
Okay,
again.
okay.
Yeah, I'm not claiming this. You're absolutely right. It's future work for us to figure out to have the slope keep going up and able to execute more distributed transactions.
Well, specific on TPCC, there's a specific transaction mix percentage that you have to maintain.
It's 10%. Yes.
Right?
Yes.
At the end there, are you maintaining that?
No. Again, it's the same number of distributed transactions for all 3 points within a single column.
And is that the fixed 10% or whatever TPCC asks us to run, right?
What's that?
So the point at 60,000 for 30 cores, is it running the TPCC with the fixed 10% distributed transaction? Or by running...
It's absolute numbers. So 10% of whatever this is, say this is like 1,500, it's 1,500 or whatever it is for all of them. Because we're executing more single partition transactions.
So you're not running 10% of distributed transaction anymore. You're now down to say...
Yeah, but the absolute number is the same.
I see what you're saying.
Yeah.
Okay.
You're at 10,000, if it's 10% of that, that's 1,000. You're up to 60,000, so 1,000 out of 60.
Yeah. Okay.
Can you always tell whether you have a distributed transaction versus a single partition?
So in case of in these workloads, we're about, I think we're almost always accurate, like 98, 99%. Yeah.
TPCC is very easily identified.
But I mean, other workloads we look at, we do the same thing as well. Yes. TM1 is a little different because you do this.
In other words, you can't always tell. So when you can't tell, you have to run it as if it's distributed.
When we can't tell, when we can't tell, it's more like it's the same thing as getting a prediction wrong. We assumed it was a single partition. We always execute a single partition. And then when it tries to touch something that we didn't know about, we just have to board and restart it. So we actually compare ourselves, what we're doing here, versus what I'll call the optimal case or the unsafe case. So this is where if you assumed that there are no conflicts and you blindly pull out whatever's in the first in the transaction queue when you want to speculatively execute something, and you don't care about serializability, this is the best you can do. So we're not that far off in terms of the optimal case, and we're maintaining serializability. So that's good. Okay, so yes.
So when you say percentage distributed transactions, so do you have an idea whether any of the, let's say if we keep the percentage of distributed transactions the same,
Yes.
but the transactions start touching more partitions. Let's say, I think in case of TPCC, it's typically 2 partitions, right?
Yes,
For
correct.
distributed transactions.
Yes.
But let's say, for example, if you start introducing 4 partition transaction or 8 partition transactions, do you expect a similar graph, or do you expect it to flatten out?
I suspect performance will get worse.
Would get worse, right? Okay.
Yeah.
It's not only the percentage of distributed transactions, but how much distribution.
Is it? I mean, if you allow the speculative one to get in, I mean,
so
you're not changing how much you're touching, right?
Yeah. So if you touch more partitions, for the Hermes case, I don't think it'd be the same trend because we're just executing more single partition transactions, so it's okay.
So the hidden assumption is that the workload is sort of there are different guys, some of which are trying to do go as fast as they can on single single transaction, and some other guys are trying to go as fast as they can on distributed ones. So if that is the case, I think this holds. Otherwise, you're not maintaining the ratio.
Correct. Yeah. Okay. Oh, yes.
So in this particular mix, you had 10% that cross partitions
Yes.
and 90% within a partition, right?
Yes.
So that means that if you just sort of did a very simple optimistic concurrency control thing here, you would commit 90% of your transactions since you have serialized access for those and they remain on a partition. Now, of course, you potentially could have a high percentage of aborts for the things that span multiple partitions. Do you have a sense of how this compares to that solution?
So your question is,
Wasn't it the naive baseline he had before?
so
Was it?
I think.
yeah. So the naive thing is you execute the single partition guy without any read-write sets, just let it fly, right? And then if you have a distributed transaction, it'll try to touch something and doesn't have the lock property at the board and restart it, or you have to move it to another node because you don't know when it comes in what node you should actually run it on.
Right, but in the next time around, you're taking locks, right?
Correct. Yes.
Right, so I'm saying, suppose you just never do that. You just keep trying to rerun it, and maybe they even starve, right? Because we haven't said anything about an SLA on being able to actually commit a transaction that you try to do, right?
Correct. So in CPCC, commit to 10% of the transactions, and I think you're suggesting if you run optimistically, you run very fast, but you'll
There may be some transactions that overcommit, but we haven't disallowed that.
Yeah, let me.
So let's do a
Yeah.
time check. So how much material do you have left?
I got 10 minutes.
You have 10 minutes?
10 minutes. Yeah. We can talk about this afterwards.
So maybe let's hold the questions to the end. And then
All right. So if you don't know this, HStore has actually been commercialized as VoltDB. It's actually another open source project that's based on our code, and it's actually used in a couple hundred installations throughout the world today. So the Japanese American Idol example I talked about in the beginning, that's actually a real world deployment of the system. And I actually found out a few weeks ago, we apparently powered the Canadian version of American Idol, which I think is just called Canadian Idol. There's a lot of people using the system to do sort of network traffic monitoring, in particular the government, the CIA and the NSA apparently love this system. They don't tell us what for, obviously, but it's other than to say that it's installed at every single telecommunication hub throughout the country, so that can make you feel warm and fuzzy at night. A lot of the
One thing that scared me the most in the last 10 years.
is what those guys. Yeah, well.
The year of your hands on the.
Yeah, so apparently they run the same amount of data through VoltDB as they run through Accumulo, which is their version of big table security stuff. But again, we don't know what they're actually doing with it. A lot of high-frequency trading guys and the high finance guys are using the system because they like the low latency properties and high throughput. So we power the Malaysian derivatives market runs entirely off of the system. And then a lot of online game companies like AOL's Games.com use the system to manage all the runtime state of players. And my personal favorite is that there's a shady offshore gambling website that I can't mention that uses the system for all their bets and wagers. So that's nice. So what did I talk about today? So I initially started off by describing a system that we built that's really optimized from the ground up to support these types of high throughput transactional workloads that we see a lot of. But then I showed how if you have just a small fraction of the workload have to touch data at multiple partitions, the performance completely breaks down. So then I showed how to use probabilistic models to be able to predict behavior of transactions and do the correct optimizations to lock the minimum resources you need in the beginning. And then I showed how to extend these models further to allow you to safely interleave single partition transactions whenever an engine is blocked because of a distributed transaction. And so it's no longer a question of can you scale up and get better performance in a system while maintaining transactions. What I showed today is exactly how to do that. So where do we go from here? For future work, I can unabashedly say that there's probably 5 or 6 new projects that we're working on in the next couple of years to extend the performance of HStore for a bunch of different things. So I'll loosely categorize these into two groups. So first, we want to look at ways to improve the scalability of the system. So I'm working with, I think, Aaron Elmore, who's coming to do here an internship with you guys this summer. It's a colleague at UCSB. We're looking at ways to have elastic deployments of the system. So right now, if you have a partition that's a hotspot and all the transactions are getting queued up there, there's nothing we can do at this point to be able to mitigate that. So we want to look at ways to identify that we're overloaded at a partition and be able to split it up into multiple pieces and migrate the data, or maybe coalesce partitions that aren't being actively used. We're also looking at ways to exploit new hardware that's coming out, and this is part of my involvement of the Big Data ICC that's headquartered in MIT, that's sort of sponsored by Intel. So in particular, we're very interested in looking at what kind of database system you want to build if you have some of the new non-volatile memory devices that are coming out. So whether this is something something like HStore, or whether you want to try different concurrency control models, we want to explore that to figure out which is the best kind of system to have. You have storage device that has the speed of reads and writes of DRAM, but the persistency of an SSD. And then we're also looking at exploiting sort of the new many-core architectures that are coming along. And then the thing that I'm probably the most excited about that's coming out the next year, which is sort of similar to your Glacier project here on the Hecatan system, is a new system model that we've been working on called anti-caching. So in anti-caching, although I just spent the last hour talking about a main memory database system, with anti-caching, we're going to go ahead and add the disk back in. And so we're going to use the anti-cache as a place to store cold data, right? The data we're not going to need anymore. And so we're going to monitor how much memory is being used at a partition, and then when we reach above a certain threshold, we're going to go ahead and evict data that has not been used recently or is unlikely to be used in the future. And we'll store that in a block storage hash table out on disk. And then we still have to maintain index information and catalog information in main memory for all the data that we've evicted. And so the main difference between a traditional database system and the anti-caching model is in a traditional system, a single record could either exist on disk or in memory at the same time. And so in our model, it's either one or the other. So now when a transactional request comes along, if it only needs to touch data that's entirely in main memory, then it executes just like before without any problems. But as soon as it tries to touch data that's been evicted, we're going to go ahead and put it into a special monitoring mode where we keep track of all the records it try to touch that are out in the anti-cache. And then when it tries to actually do something with that data, either modify it or send it back to the application, we're going to abort it, roll back any changes that it had. In a separate thread, asynchronously, we're going to go fetch in the blocks that it needs to get the data from, merge that into main memory. All the while, we're still going to execute other transactions, not block them. And then once we know that our data has been merged in, we update our indexes, and we can now restart this transaction, and it runs just like before. So again, the key thing about this is now we're able to support databases that are larger than the amount of memory on a single machine. And so we've done some additional experiments where we've taken TPCC, this time with 100% single partition transactions for a 10 gigabyte database. And we want to scale up how much memory we're going to give the system. And we see when we use MySQL, the performance isn't so great. Using MySQL with memcache for certain read operations, the performance isn't that much better because TPCC really can't take advantage of sort of the caching properties, the read-write properties you get from memcache. But now when we use HStore, you see that performance does not degrade that much for databases that are 8 times the amount of memory that is available to the system at a single node. So this is pretty exciting work here. The other stuff we're looking to do is we want to expand the type of workloads we want to run on the HStore system. So we're with a colleague at Brown, we're looking how to integrate stream processing primitives or continuous queries as a first-class entity directly in the system. So we have a mix of streaming data and transactional data and sort of intertwine them together. And then sort of related to what all the discussion was for distributed transactions, we want to look at how can we improve the performance of the system for workloads that are not easily partitionable. So if we add more distributed transactions, how can we make the system perform better? And so this is we want to do things like batching and other techniques to amortize the cost of acquiring these locks at all these different partitions. I'm also looking at getting back involved in working with scientists to apply database techniques for scientific workloads. So this is possibly building a whole separate system that's really optimized for their types of workloads, right? Because a lot of them are sort of running these Fortran scripts or C scripts, running MPI programs that don't take advantage of the kind of things that we know about in the database world. And then lastly, the thing that the next major trend I see, which I'm sure you guys are aware of here, is adding support for these front-end main memory systems to do real-time analytical operations. So now we want to be able to do the longer-running queries that have to touch more data without having to run that as a distributed transaction that needs to slow down the entire system. So a lot of the game companies care about this kind of thing. They have the front-end system is maintaining all the runtime state of players, and they want to be able to say, here's the top 10 players for a bunch of different metrics. So instead of shoving that off into your back-end system or Hadoop or whatever, running the analytical query there and then shoving it forward, we want to be able to do that directly in the front end. And so to do this, we want to apply techniques like using hybrid storage models or hybrid nodes and applying techniques like relaxed consistency guarantees of these analytical queries. Now, these aren't new techniques, but we want to sort of come up with clever ways to combine them together. And again, leverage other machine learning techniques to make the system do this automatically. Because that's really the main takeaway for what my research is all about. It's really having the database system know as much as possible about what the application is trying to do and what the workload is trying to do, and be able to have the system go faster and get better performance because of it. So I want to thank everyone coming today. I'm happy to answer any more questions. And there's also a website set up for the HShore system where more information about the documentation about all the things that I talked about today. So thank you.
Any questions?
You measured TPCE.
Yeah, so yes, so TPCE won't work well on this. You're absolutely right. I will say, though, from the VoltDB guys, what they tell us is a lot of the workloads, there's very, very few workloads that they see are complex as TPCE. TPCC is actually very representative of what's out there in terms of the size and complexity. But you're right, TPCE won't work well on this system. And that's one of the things we want to look at in the future. Yes?
So TPCC was designed as a benchmark, and it's got uniformly distributed data and
Yes.
carefully designed,
Yes.
which is not true in most cases.
Correct, yes.
And so the partitioning might result in hotspots of this sort.
Correct, yes.
And the other thing is that it's designed with Oracle in mind, which is to say it's also designed so that it runs just fine using snapshot isolation.
Yes.
So TPCC is, interesting benchmark, but it certainly isn't conclusive in terms of anything.
Oh, absolutely. So we've done, I didn't talk about that, we've done other experiments. I mean, with Carlo and I, we have a whole benchmark suite with a bunch of different OLTP workloads that we tried it out. And again, TPCE is an excellent example of something that won't work well in this. Anything like looks like a social graph, Twitter, Facebook, that stuff, that won't work well in this. But again, I would say from what I've seen in industry, working with the VoltDB guys, TPCC is actually very representative for a large number of applications that simply it doesn't, they're not getting the performance they want using times 10 or other things, and they're switching to something like VoltDB.
Okay.
All right, thanks guys.